and almost everything else. And then this afternoon, the lab will be running some Monte Carlo codes to see how things work there, and you'll be able to compare this code with Hydrolite and also do some 3D problems and so on. So, and then the second lecture, unless Colin shows up, will be on color and camouflage and visibility and things like that. So that's more of a fun little lecture. So, whoops. Okay, so it's rather ironic. That is exactly what I was doing last Saturday, was debugging the Monte Carlo code for this class. And anyway, Monte Carlo techniques got invented. You guys think I'm too old for even remember things like that, but that's not true. After the Second World War, they needed to develop techniques to track neutrons as they bounced around inside chunks of uranium, obviously for making bombs. But since that was all highly classified, they needed some term for it, and somebody said, well, since this is all, actually a mathematician named Metropolis said, well, what we're doing here is all based on probability theory, and I like to go to the Monte Carlo casino in Monaco, and that's all probability theory for gambling. Let's just code name this Monte Carlo techniques. So that's how it got started. And this photo of me was taken at the casino in Monte Carlo, where in the very inner sanctum, there's roulette wheels and stuff, where the minimum bet is $10,000. Well, that's the price of Hydrolite. So I figured, well, I'll just take a stack of Hydrolite CDs and I'll use those as $10,000 chips. But it didn't work. They threw me out. So anyway, here's the story. Hydrolite, which you're now familiar with, can only solve one-dimensional problems. Things can vary with depth, but not horizontally. Well, the world is full of three-dimensional radiative transfer problems. So here's one, for example, here's the sea surface. If the bottom is sloping, well, that's not a 3D problem. It's not horizontally homogeneous. Or maybe the bottom is level, but this half is sand and this part is seagrass. Well, once again, that's not horizontally homogeneous in the boundary conditions. I've been using a version of the code we'll use this afternoon for simulating light fields onto three-dimensional coral reefs. So this is level here. There's typically what's called the forereef, and then there's a reef wall. And so we're interested in, like, what's the light field on the wall of the reef here as a function of sun angle and depth and so forth. Well, that's inherently a three-dimensional problem. You can't solve it with Hydrolite. We also can have little overhangs and say, well, how much light is getting up onto the bottom of this little overhanging bit of reef. So 3D problems like this, you can solve with Monte Carlo techniques, and that's what they're mostly used for. Here's some other 3D things. You've got an object in the water, and you want to know, can I see this? So there's this, and we'll see in the next lecture, when you're up here and you want to say, can I see this? You're looking at the radiance from this object compared to the radiance right next to it, and, is there enough contrast to see it? Well, that's a 3D problem. If you have a ship here, there's a shadow, you drop your instruments in the water, they go through the ship shadow. That's not really the same as what you would measure in the open ocean without the ship there. So that's the sort of thing you can play with Monte Carlo techniques. And so the bottom line is that this term Monte Carlo refers to ways you can solve problems using probability theory and random numbers if you have some process that is some way random. So you have, in the case of optics, you've got some probability of how far a photon will go, then it scatters, then there's some probability of what angle it will go off into. If it interacts, there's a chance it'll be absorbed, there's a chance it'll be scattered, and so on. And so it's a big string of random events. How far the photon goes, is it absorbed, is it scattered? If it's scattered, what's the scattering angle, and so forth. So the idea is that you have some process where you know the probability of each separate thing, like how far the photon goes or what the scattering angle is, and you can string those probabilities together and then get the probability of the overall process. So this is used in basically everything from optics to economics to medicine to whatever. And economists will run probabilistic or Monte Carlo simulations of what's going to happen to the economy. Well, there's some chance Trump will be reelected and that'll do this. There's a chance he won't be and that'll do something else. There's a chance he's going to start a war, very high chance actually. And well, what will that do to the economy? And so on and so on. And there's a chance that there will be a massive power blackout and it'll knock the economy down by 5% next year. So put that probability in. And then you eventually come up with these scenarios of, with whatever probability, this is what the economy will look like in 5 years or 10 years, whatever it is. So in optics, as I said, we talk about light rays. If you read the literature, people will talk about photons or photon packets, but it's all the sort of same thing, and being, going a certain distance, being scattered and so forth. And then you run this scenario often millions and millions of times. You start a new photon, you see how far it goes at random, you see what angle it scatters at random, and so on, and do maybe 1 million photons and then average the results together to get an idea of what you would measure in nature. And so then you can estimate radiances, near radiances, and so forth. And that's what we'll do in the lab. So the basic idea is first figure out, what it is that nature's doing in how light rays are propagated and scattered and so on. And we'll treat these light rays or photons as individual things, and one's independent from the next one. And then you'll basically build up a solution to the radiative transfer equation, one photon or one ray at a time. And then to do that, we'll use basic probability theory and random number generators. So what I'll do here, for those of you who didn't take your undergraduate probability class like you should have, we'll review the basic ideas of probability theory that we'll need here, talk briefly about random number generators, cumulative distribution functions, Monte Carlo noise, and then there's a whole series of webbook pages on Monte Carlo techniques, of which we're going to cover basically the first page, and then there's a bunch of fancier things you can do that we won't talk about. Okay, so here's the basic idea. There's a thing called the probability distribution function or probability density function, and it's a non-negative function such that the probability that some variable x is between x and x plus dx is this PDF times dx. So, for example, if x is, say, the height of all humans, then x is measured in meters, and you'd have some probability here. Okay, so no people are less than, say, 40 centimeters long, because that's where you're born. Nobody's more than 3 meters high, so there's nothing out there. And then, there's this distribution of heights here. And the idea is, if I want to know how many people, what's the probability if I select somebody at random from the whole world's population, what's the probability that they'll be, say, between 1 meter and 1.3 meters high? Well, you take this distribution, you integrate from 1 to 1.3 meters of the PDF of x dx. And so this number might be 0.2. And that's going to be then the probability of somebody being from this height to this height. Now, everybody has some height. So if you integrate from 0 to infinity, the PDF has to integrate to 1. There's a probability you'll have some height between 0 and infinity. Or in this case, you could integrate from 0 to 3, say, and you'll still get 1. So notice that this, whatever the units are here, the PDF is 1 over those units, because you're going to integrate. In this case, it's 1 over meters times meters gives you a non-dimensional probability, which is some number between 0 and 1. So that's how PDFs work. And then there's a thing called the cumulative distribution function, which is you integrate the PDF from 0 up to some value, and that's the CDF. So here's our PDF, and then if we just start integrating this, the CDF goes from 0 and then builds up to 1, and then after here, the PDF is 0, so nothing more contributes, and the CDF stays equal to 1. Okay, so then if you think back here, well, what's the probability that somebody's between 1 and 1.3 meters high? Well, if you think about it, that's just the CDF of 1.3 minus the CDF at 1. If you just go back to here, and you could say, well, the probability of being between 0 and 1.3, that would be the CDF of 1.3. The probability of being between 0 and 1, that's this integral out to here, which is the CDF of 1. And so integrated over this much minus integrated over this much is what I'm interested in. Okay, so that's the way CDF sequences work. And so they always, their last value out here, they always go to 1. So just telling you once again, probability of some value is 1. Okay, so then random numbers. We're going to have what's called a uniform 0-1 random number generator. And that's basically going to be a computer program that puts out a string of unrelated random numbers between 0 and 1, and we're going to use that now to actually generate things like how far a photon goes or what the scattering angle is. So if you look at the PDF of a uniform 0-1 random number generator, well, it's defined, it's non-zero between 0 and 1, and there it's equal to 1, and you never get a number less than 0 or a number more than 1. So this little guy's PDF is simply this little function right there. And so here I just used one of the built-in ones, and every computer language has a dozen different random number generators that you can use. So here I just generated 1,000,000 random numbers. The first bunch are seen here, and then I just bin them by bins of 0.01 wide, so 0.01 times, and so I have 100 bins, and just looked at how many times, what frequency or what fraction of the total did the random number occur in these little bins. And you can see it's fairly uniform across here. The more and more numbers you generate, the straighter this line will become. But you can see there's just as much chance that I'll get a number between 6 and 6.01 as there is between, say, 0.2 and 0.21. So that's what a random number generator looks like. Now, in general, these things are not really random number generators on computers. They will repeat the cycle of numbers, but it'll usually be after like 10 to the 32nd numbers, and we only need to generate 1,000,000 numbers, so you're okay. So technically they're called pseudo-random number generators, but random is good enough for us. So that's how those things work. And then now we have this idea of a light ray, and which is, I'm going to say my Monte Carlo code does ray tracing. Well, light rays are just this kind of hypothetical little construction that's the direction of this light ray arrow, if you wish, at any point shows you the direction the light's going at that point at that time. So light rays are sort of the basis for a lot of optical engineering. If you want to design camera lenses or something, they start out and here's an actual, some kind of fisheye camera lens, and they use ray tracing to shoot a ray in here and follow it all through the lenses as it reflects and refracts and see where it's going to end up back on the focal plane here. So these kinds of things are how you do those kinds of calculations. We're going to do the same thing in the ocean. And Monte Carlo code, we're all here in the domain of geometric optics. So we're not looking at diffraction and interference patterns and things like that. We're just in sort of classical physics where you have big objects and you don't look at these gory details. So anyway, that's the idea of a ray. Then we'll now trace the rays through the water. So here's the question now. What do we use for the PDF to generate the distance a ray goes? For example, I shine this light through the water. Well, the photon or the ray is going to go some distance, interact, and then do something else. So how do I determine that distance? Well, you remember Beer's law. If we have a collimated beam of light in a dark homogeneous ocean, Beer's law says the radiance at distance r is the value at 0 times e to the minus cr, or e to the minus tau, where tau is the optical path length, which is beam attenuation times the physical one. So if you think about it long enough, you can convince yourself that in order to reproduce this basic observed bit of optics that you played with in the lab, if we take the PDF for a ray going a certain distance as being e to the minus tau right here, then this PDF will end up reproducing this decay of radiance as you add together the results from many, many, many different rays or photons. So I'm just going to claim here that the PDF for generating photon path lengths is really just e to the minus tau, or e to the minus cz, if you want to do it in terms of meters. So now we say, well, okay, if that's my PDF, then how do I pick the random number and use that some way to determine how far the ray goes? Well, you can think of it this way. We're going to have the probability that a ray will go from some distance 0 to tau. That's the CDF here. And we can think of, instead of using the variable tau, let's use the random number. And so the probability that the ray goes a distance tau is going to be the same probability that my random number will have some value r. So in other words, if r is a 0, then the photon goes 0 path length. If r is 1, the photon will go an infinite distance. So there's this little kind of a change of variables here, where the probability that my random number is between r and r plus dr is the same as the probability that my photon path length is between tau and tau plus d tau. Might not be quite obvious, but that's the way it works. So it's really a change of variables between optical path length and random number. Well, the P of r here is just this uniform 0 to 1 random number generator. So if we plug in here and get the CDF of this, well, the CDF for the random number is 0 to r integral of the PDF, but the PDF is the uniform 0 to 1. And so that's just 1 for r between 0 and 1. So just 1 integrated over dr, that just integrates to r. The CDF over here, well, for this PDF, you integrate that, the CDF is 1 minus tau. So in terms of r and tau, that's the relation that'll give me that decay of radiance. So if we just solve this equation right here for tau in terms of r, we get this little thing here. Or if I solve for tau, it's tau is minus log of 1 minus r. Well, little trick, since r is uniform 0 to 1, so is 1 minus r. So I could just write this as tau is minus log r. So I draw a random number r between 0 and 1, plug it in here. Log is negative value between 0 and 1, and that makes it positive. So that gives me the optical distance the photon will go. And if I want to use not optical distance but physical distance, then tau is c times the distance r, so I would just have minus 1 over c log r. So that's how I generate how far this ray is going to go at random. Okay, let's see. Then there's this little thing which we've just seen. It's called the fundamental principle of Monte Carlo simulation. And, the mathematicians give it this fancy name, and it's all in capitals. But it basically says, you give me a PDF, I'll compute the CDF. And then I solve the equation, random number equals CDF. I solve it for x, and that gives me an x that obeys the corresponding PDF, whatever the PDF is. So you give me the PDF, I compute the CDF, draw the R, come over here, wherever that is, that comes down and it gives me the value of the random number. So that's the fundamental thing that goes on in Monte Carlo simulation. So the whole basic idea is you have to figure out what the PDF is for whatever your variable of interest is, compute the corresponding CDF, draw a random number, solve this equation here, you get the x value, and then cycle through this a zillion times and then average all the results together and you get your answer. Okay, so there's a little thing called the mean free path, which is the distance a ray travels on average. So for one ray and one little path, there's our PDF. And now anytime in probability theory when you have a PDF and you want to know the average of the variable, it's just computed by that variable times its PDF integrated over the full range of whatever, in this case tau goes from 0 to infinity. So the mean free path, or the average distance that a ray travels, is now tau times our PDF here is e to the minus tau. Do the arithmetic there, and this turns out to be 1. So the mean free path, on average, a photon goes 1 optical path length. Or since tau is CR, we can say that R is 1 over C meters. So on average, you give me the beam attenuation coefficient at 550 nanometers, it's 0.1. On average, photons go 10 meters in that particular water body at that wavelength. And then it's kind of neat that what's the variance about this mean? Well, the variance is by definition, you take the variable minus its average, square it, times the PDF, integrate it, you do the calculus, and once again it turns out to be 1. So if we, and the variance of course is a squared, if we take the square root, sigma, to get the standard deviation, well, square root of 1 is 1. So the standard deviation is also 1 over the beam attenuation. Very kind of unusual thing, and you can play with that in the lab today until you convince yourself that it's actually true. Okay, anyway, this is called the mean free path in optics. Okay, so now we need to determine a scattering angle. We shot the ray out, went 2.3 meters, now we have to decide, it's scattered, so what direction does it go? Well, back to our old coordinate system here, we get to pick the coordinate system. Ray is going in this direction, it scatters into this direction and through some scattering angle. Actually, it starts in this direction and scatters into that one, and there's the scattering angle. So now we have to figure out what do we use for the PDF to get this scattering angle at random. Well, scattering's inherently three-dimensional, so we've been assuming that it's isotropically constant or symmetric, so it only depends on the polar angle. But in reality, it is all going off in some azimuthal direction. So I'm going to sort of have to account for that. Psi is the polar scattering angle, and then chi here is the azimuthal scattering angle that we'll have to determine each one of those randomly in order to decide where the light goes. So we can take our volume scattering phase function and we can interpret that as a PDF that takes me from the initial direction to the final direction, and then we're going to integrate that over solid angle, because remember this is scattering per unit solid angle centered on direction psi and chi. So we're going to have to integrate over all solid angles to get the total probability is 1 that this initial direction will be scattered into some direction, whatever that is. And we know it's going to go somewhere. So the integral of this over all 4 pi steradians is going to be 1. And one of the requirements for a PDF is that you integrate over the range of variables. It has to be 1. There's a probability of 1 that it's going to go in some direction. And we remember our old friend here, element of solid angle is sine psi, d psi, d chi. Okay, so how this works now is, let's see what I do next here, yeah. For isotropic media, that means it's the same optical properties in any direction. If you're in the water looking around, this beam C is the same as beam C for that direction. Okay, then psi and chi, and if it's unpolarized light, psi and chi are independent. So this is really what's called a bivariate distribution or bivariate PDF. It's 2 variables at once going to 2 variables at once. But if these 2 variables are independent, this can be written as a product of a PDF for one times the PDF for the second. So we're going to take, and also when we write out that d omega is sine psi d psi d chi, this integral of that whole thing has to be 1. Okay, so what we're going to say is here's our bivariate PDF with both variables mixed in together. We're going to view that as one PDF for angle psi and times d psi and one for angle chi integrated over the chi variables. So the azimuthal angle is going to go from 0 to 2 pi. If we assume things are azimuthally symmetric, then any angle from 0 to 2 pi is equally likely. And so I kind of say, oh, okay, I get it. The probability of going through an angle chi is just 1 over 2 pi. It's equally likely to have any value from 0 to 2 pi. So the CDF, if I integrate that, is just chi over 2 pi. Set that equal to r and solve it. And that says to determine the azimuthal angle, draw the value r, multiply it by 2 pi, and you get the angle in radians. Okay, cool. So now I figured out the PDF here for this guy. Well, what that leaves me is that psi then, if I plug this in, must be 2 pi beta tilde times sine psi. And remember, as we've been using this, if you integrate the phase function over solid angle and 2 pi, because it's azimuthally symmetric, that equals to 1. Okay, so this thing right here is a probability distribution function. It integrates to 1 when you integrate it over its angle. Okay, so now to find the polar scattering angle psi, we're going to take the phase function times sine psi, that's our PDF. We're going to integrate from 0 out to angle psi. That gives us the CDF, and then the 2 pi is in there. And then, so that's the CDF of psi, and then we draw the random number, we solve the CDF for the angle psi in terms of the random number. That's the general procedure. So what's this look like in a particular example? Well, if we have isotropic scattering, beta tilde is 1 over 4 pi. It's equally likely to go into any solid angle. And if we come in here, we plug in right here, 1 over 4 pi, so that gives us a 1 over half here, and integrate the sine, integrates into minus cosine, evaluate it, and solve, and you get that the angle psi is determined by the inverse cosine of 1 minus 2 times whatever the random number was. It looks a little strange, but that's what works. Now, here's 2 simulations. One where I did an equal distribution of points in the direction psi. And so I basically said that psi is determined by a uniform random number generator where any angle from 0 to 180 is equally likely. Fine. And then I determine the azimuthal angles. Okay, you plot that up and you look at it and you say something's not right because there's a whole lot of points right here at the North Pole. The incident direction is going this way and then it scatters off into some other direction. And if you look at the South Pole, which you can't see here, there's a lot of points at the South Pole. So you say, well, something's not quite right. I should be getting equal numbers of rays going in every direction if it's isotropic scattering. Well, isotropic scattering doesn't mean equally likely to have any polar scattering angle. It's equally likely to have any element of solid angle. So then if you do what we have right here, draw the random numbers, get the size, plot the size and the chi's, now you get a distribution of directions here where anywhere you look, it's kind of equally likely that you're going to find a point. So if I pick a little solid angle, you know, 1/10 of a steradian here and it has 50 points, and 1/10 of a steradian here or over here, they'll all have, you know, roughly 50 points. Here you looks like you have 200 points, and here maybe you only have 30. So keep in mind that scattering is about going into a solid angle, not going into a particular direction like psi. So that's why you sometimes get these funny looking equations for the angle you're going to pick, but that angle is biased in a sense so that you get fewer at the North Pole and more towards the equator. That's where the cosine comes in, and that's what gives you equal distributions in solid angle, because a little solid angle here is, you know, a delta theta of 10 degrees and a delta phi of 15. That little box is smaller than the box down here of the same angular size. Okay, a little weird, but that's the way it works. So then we want to trace, you know, ray packets or ray bundles or photon packets, and there's a couple of ways that you could do this. One of them is you would say, well, I've got my source here, it's sending out light. So I draw a random number, light goes this far, then I decide it scatters, it goes off in this direction, but then I decide it's absorbed. Well, I now have to throw this photon away because an absorbed photon that never makes it to my detector doesn't end up contributing anything to the answer. So I wasted this calculation. On the other hand, this photon comes out, it scatters again, it goes over to my detector, and I say, okay, I recorded a photon here, that's going to contribute to my answer. Now, one way you could do this is, if you remember, the albedo of single scattering is the probability that a ray will be scattered rather than absorbed. So if the albedo is 1, B is equal to C, that says the rays are always scattered, there's no absorption. If the albedo were 0, B is 0, C is whatever, and that would say every time a photon interacts, it's absorbed. And then the real world is in between. Okay, so what nature does is it says, draw my random number, shoot the photon out, and then I'll draw a random number, and if R is greater than omega naught, the ray or the photon will be absorbed, and then I'll stop and I'll generate another one. So that's this case. Or if the random number is less than or equal to omega naught, then I'll say the ray is scattered, and I'll compute the scattering angles and carry on with another ray. Now, the problem with that mimics what nature does, but the problem is you're throwing away some of the photons that you spent computer time to generate them and trace them, and they never made it to your detector. Okay, so nature can afford to waste photons, but we can't. So another way to do it is to say, let's assume that each ray here starts out with some weight of 1. And then every time it interacts, we'll assume it's scattered, but we'll decrease the weight by omega naught. So if you thought of this red line as being 1,000,000 rays, then some fraction of them would be absorbed and the others would go on. And so at each scattering interaction, you multiply the current weight by omega naught. And then by the time you get over here, the weight would be, let's say in this case, there's been 1, 2, 3, 4 scatterings. The weight of the red ray here would be omega naught to the 4th. So if omega naught were 0.9, then 9 nines is 0.81, 81. So that would be like 60% of the initial power would have made it over here. And for the green one, it does 1, 2, 3 scatterings. So the weight's omega naught, 1, 2 scatterings, omega naught squared. So if omega naught were 0.9, you would be getting 81% of the energy made it through here. So in this case, you never kill a photon. Now, some of them may go off and miss your detector. You just have to live with that. But in reality, some of these would have been absorbed, but now we just let them keep scattering, but we decrease their weight. And then at the end, we say, okay, we traced 1,000,000 photons here. They each had weight 1, and the final weights over here were, so we have a weight of 1,000,000. Over here, the final weight is, say, 500,000. Well, divide by the initial value, and that says half of the energy made it over here, and that lets me figure out what the irradiance was onto the detector. And we're generally going to keep track of that in lots of little bins here, so I can get radiance as a function of angle, or I can get total irradiance, whatever it happens to be. And then typically, when a photon goes off wherever, we'll eventually drop it when its weight gets to be less than something like 10 to the minus 6th or 10 to the minus 8th, and then just throw it away and start over with a new ray. Okay, so that's the sort of thing that works there. Here's just a visualization of ray paths. So I had a source down here shooting out photons all in the same direction, and then they start scattering around. Let's see, did I say, okay, so I've emitted 1,000, omega naught was 0.8, I'm using a Fourier-Farrand phase function, and so anyway, these guys start out, and then they start scattering around, and so here's, X, Y, and the distance they're going, Z. So you kind of see this big cloud of actual ray paths where you can see there's been a lot of scatterings here, and then finally the weight is less than 10 to the minus 8th or whatever it was. If I looked only at just the rays that have been scattered once, well, here's what you see. And one of the kind of nice things about Monte Carlo is you can trace these photon packets from scattering to scattering to scattering. And you could say, okay, here's all orders of multiple scattering before the weight became negligible. Here's what it looked like just for single scattering. Or you could do just 2 scatterings. And you get a feeling for what the light is doing ray by ray, which you don't get out of something like hydrolite, but you can get from Monte Carlo. And you can see, here's the occasional one of these guys just goes way off to wherever. And then some of them don't make it very far at all. Okay, here's just another view. I've sent in 10,000 photons. I guess this is 10 optical distances here from here to the target. And then I just look at where do the rays hit out here. Well, I plotted, here's XY, here's XY here. I just drew a circle here where this is 30 degrees off axis, and you can see most of the rays are going off. They scatter a little bit. They're mostly in this sort of like 30 degree zone. Some of them go further out, and almost all of them are on this plot. Occasionally one will go off somewhere else. So you can kind of look at this and get a feeling for kind of what the light is doing. If I take this data here and I plotted the percent of photons that go an optical distance tau, well, my target was 10 optical distances away, so they all had to go at least 10. Even if they just went straight across, they're going 10. But some of them, of course, they're scattering, and so they're going a greater optical distance in order to get to the target, which is 10 optical depths away. So you see most of them are going somewhere between 10 and 11, some between 11 and 12, and some of them are maybe even going out to like 20 optical distances to get from the 10 from the source to the target. So you can look at things like that, get a feeling for, you remember you have to do like, what's it called, the path length correction in a spectrophotometer to account for multiple scattering in the filter pad. It doesn't just go straight through, the light bounces around. Well, that's the sort of thing you can look at from Monte Carlo, and you could take this and find what's the average photon path length going through my medium. In this case it's water, but it could have been a filter pad, and you could come up with a scattering path length correction. Here I also plotted the number of scatterings that it took to get from the source to the receiver, and basically none of them made it in just one or two, and then sort of 4 or 5, whatever. Most of them took about 6 or 7 scatterings to get from here over to here, and then a few of them might have taken 18 or 20. So this kind of info you can get from Monte Carlo simulations. Okay, then the business of Monte Carlo noise. Because we're doing random simulations here, there's going to be statistical noise, which usually gets called Monte Carlo noise. So here I did 10 runs, independent runs, where I generated 10,000 rays in each run. And then I looked at, I have a detector out there, I don't remember if it's the same one we had in the previous simulation, but anyway, I had a detector, and I said, well, what fraction of the emitted power made it to my detector? And you can see the numbers here. This is like 0.01, so 1%, 1.2%, 1.4%. So in like this run, the value was somewhere about 0.9% of the power made it to the detector. Out here, it was like 1.2% of the power made it to the detector. And there were 10 runs, so that's what the results came out to be. Now I do 100 runs, same thing. I get this. I do 1,000 runs, I do 10,000 runs, each run still having 10,000 photons. And now you see this distribution's kind of starting to look normal. Here it's hard to say, maybe it could be normal, it's starting to look normal. Now you're kind of convinced that it's a normal distribution. And so the bottom line is you do more and more runs, the distribution of the results, whatever they happen to be, will always approach a Gaussian, even though your underlying PDF is not Gaussian. Here our underlying PDF was this exponential for the distance traveled. It was this other, some kind of inverse cosine thing for the scattering angle. But then the distribution about the mean will always be Gaussian. It's a very strange result. And that's what's called the central limit theorem in probability theory. Now, each of these runs had 10,000 photons emitted. And I get this distribution. So I might say, well, the average here is something like 0.015 with this standard deviation. Well, I need to get a more accurate answer, because if I just do one run, I could have this value, this value, this value. So what do I do to get a more accurate simulation with less noise? It's not doing more runs, it's do more photons in each run, and then you're going to average those together to get this mean. Here, it's 10,000 independent experiments with 10,000 photons each. So I'm always averaging 10,000 photons together, and that gave me this distribution. If I want to get a more accurate answer, then I need to do more photons. So here I've traced not 10,000, but 100,000 photons in each run, and it still goes to the normal distribution. It's still centered on something like 0.011, but now the standard deviation is smaller because I've averaged more photons together in each simulation. So you kind of keep in mind that result, that if you need a more accurate Monte Carlo estimate, you trace more photons for each run. And there's a very general result in probability theory that says as you do more and more, in this case, trace more and more photons, the variance is proportional to the number of rays detected, or the standard deviation is proportional to 1 over the square root of the number of rays. So if we're back here and we say, oh, this is too much variance or too big a standard deviation, I want to cut that by a factor of 10, and I've traced 10,000 here, I have to trace 1,000,000 runs to cut this by a factor of 10. So 1 over square root of 1,000,000 versus 1 over square root of 10,000. So to decrease your error in your estimates, and you want to cut that by 10, you have to trace 100 times as many photons. And that's, once again, a very general result from statistics, whether it's photons you're tracing or anything else. Okay, so then that's, there's a whole bunch of techniques that generally get called variance reduction techniques. And they're tricks you can do to squeeze down the variance in the answer and get a more accurate answer without spending any more computer time. And that's what most of the pages on the website are all about. And so kind of what you do with Monte Carlo, you need to write a code. You sit down, you figure out, what does nature do? Okay, maybe you write the code, computes that. And then you sit down and say, now how can I get the same answer with less calculation? And you come up with some trick. Well, I'll show you one of those in a minute. Okay, and the goal here, which you'll probably never attain, is to never waste a ray. That is, don't compute a ray path that never makes it to your instrument, because that doesn't contribute to the answer, it's just wasted computation. Okay, so there's a technique called backward Monte Carlo, or sometimes reverse Monte Carlo, where you can think of in the real world, okay, here's a sea surface, here's the bottom. We haven't talked about BRDFs yet. That's bidirectional reflectance distribution function. It's basically the probability that if a ray hits a surface, it'll go off in some direction. BRDF is the surface equivalent of a volume scattering function, and they're just different functions is all. So anyway, you can think of, well, okay, I've got a sensor in the water here. It's looking down here, and here comes a photon from the sky. It gets through the surface. It bounces off the bottom. It goes off over here, and it's never recorded by my sensor. In this case, my sensor has some small viewing direction, so maybe it hits the sensor, but it's outside that viewing direction, or maybe it just misses the sensor totally. So if I start the ray up in the sky, and we trace it down, bounce it off the bottom, I've done a lot of computation, and I didn't get any contribution to the answer. But what's cool, if I have, let's say, the sky radiance up here, sends in a photon, follows this path length, and does go into my sensor, when maybe of the energy that started out up here, 2% makes it to my sensor. Well, there's a little thing called the principle of electromagnetic reciprocity, once again, all capital letters and very fancy, that says if I have a photon that traces this path in this direction, if I start a photon here in the opposite direction, it will retrace exactly the same path. Okay, So what I can do is, what nature does, it says I'm going to send this radiance from the sky along this path, and 2% of that radiance makes it to my detector. Well, I'm going to start a ray from the detector and send it off in this direction, and it'll go back to the sky at the same spot, and 2% of the energy that leaves here will make it back to the sky. Now, what I'm doing is I'm sending all of my light out of the detector, so I never have a photon that misses the detector. I'm just tracing things backwards. And then I say, rather than starting with a weight of 1 here and getting 2% here, I'll start with 1 here and get 2% here. And then I'll take the sky radiance right here, and I'll take 2% of that sky radiance, and that's how much would have made it to my sensor. So here's kind of how it works in practice. If we have, let's say we want to measure planar radiance, we have a cosine detector, all the light's coming in from the sky. Now I'm going to send the light out in a cosine pattern and see where it goes and record where it ends up in the sky. So here's the same little sky theta phi pattern that hydrolite uses. And so I'm going to pick a ray here, send it out in a pattern that's proportional to the cosine of the angle to the normal, just like the sensitivity of the detector is proportional to the cosine of the angle to the normal. And I'll shoot these rays out, and this one goes to there, and maybe this one goes there, and now and then one does go off, and it gets thrown away. But most of my rays are at least heading off towards the sky and will eventually make it up here. Then I take however much energy, let's say 1% goes here, 2% goes here, etc. I trace millions of rays. I find out that distribution of energy that makes it from the detector to the sky. Then I can come along and say, okay, if the sun was here, I generate a sky radiance distribution, and now I know this was a really bright sun and 1% of the light or energy went here. I'll take 1% of that really bright sunlight radiance. That'll go into my detector. Maybe 0.5% goes here, but that's blue sky. It's not very much energy, but I'll take the 0.5% times that number, and that's what I would have detected. So it's a way to do things and get more photons contributing to your answer than if you just shot rays from the sky down, and they might or might not go into your detector. It depends on if it's planar radiance or what. Okay, so the code we'll play with this afternoon is a backward Monte Carlo code. And the nice thing about it is I can do one round of ray tracing to get the distribution of energy from here into my sky, and then I can say, well, if the sun was here, this is the answer I would have gotten. If the sun was over here, well, that's the answer I would have gotten. And so I can get all sun angles and all sky conditions from one set of ray tracing. And so that's, whereas in hydrolite, you run hydrolite, you put in one sun angle at a time, and that's it. And then you want another sun angle, you do another hydrolite run. Now, as you'll see this afternoon, the catch is when you do that one hydrolite run, you get all the radiometric variables at all the depths and all the wavelengths and so on. Here, you're going to get any sky condition you want, but only one type of sensor at one depth at one wavelength per Monte Carlo run. Okay, so here's a couple of examples of people using backward Monte Carlo code. So this is Xiaoling Shang and probably Zhongping Li and whoever else. So they wanted to take one of Zhongping's, cone radiometer things to measure remote sensing reflectance, and they wanted to stick it on the side of one of these gizmos made by Satlantic. What's that called? Yeah, the HyperPro. You guys had one of those in the lab. So they wanted to stick this thing on the side of the HyperPro, stick it at the surface, do little thing, but of course they want to correct for the shading of this and also for the effect of this thing, which is going to maybe put a shadow into the water. So they set up this big backward Monte Carlo code where they shoot photons out of the instrument. They go bouncing around in the water. Some of them make it up to the sky. Some of them don't. Some of them come over and hit the instrument, and that gets the instrument effect. So that's what they're doing in their paper here. And they've built in all the exact geometry of this thing, all these little cylinders and their radii and length and the angles of the cone. Everything has to get built in for each Monte Carlo simulation. And even though it's in principle, it's very simple, in practice it can be a real mess to program in the geometry, because in this case, or actually let's just talk about the code you're going to run today. So there's this coral reef here that looks like that. And then let's say I've got a photon here and it goes here and it scatters in this direction. Now at first all I know is it's going in this direction, and then I figure out it goes this far. But then in the programming I have to say, okay, it went this far, so that's 5 meters. But this direction here, it intersects here, it intersects here, it intersects here. So I have to look and compute the distance from here to here, here to here, here to here, here to here, and then say, did it hit the wall before the photon was at the end? Well, in this case, the photon went this far, and that was before it hit anything. So now I can scatter it off in another direction. But if my photon, as I originally generated it, went this far, then I say I'm going to have to compute this distance, and then this distance, and this one. And then I say, oh, it hit here before it got to the end of where it would have gone into water. So now I have to do the BRDF thing and send that photon out. Or if the photon had been up here going in this direction, then I'd have to say, well, it intersected the top here, it intersected the wall here, it intersected the surface up here, and then I check and I say, but this point here is to the right of the coral reef, this point here is to the top, so it really was in the water all the way. And all of that is like simple geometry, but enormously messy logic to build into the code all of those little calculations and decisions. And that's why the Monte Carlo codes can take a long time to run, especially if you have a geometry that's this complex. Because when they send this photon out and it scatters here, they have to check, did this photon here hit this thing? Did it hit this? Did it hit this? Just a whole lot of if in the code, and the answer was no, it finally made it through to the sky. In this one, it comes down, it scatters, did it hit this? No. Did it hit this? No. Did it hit this surface here? Yes. Oh, okay. So now we can either kill the photon if this were black, or we can send it off in another direction. So every Monte Carlo simulation is a new computer program. It's a real mess. But with Hydrolite or some other code like that, you kind of write the code once, and then you can put in depth dependence of IOPs and all of that, and you don't have to write a new computer program. But for 3D problems, every 3D problem is different. Okay, so then what they did when they programmed this thing up, the first thing they did was they compared their code with Hydrolite when there's no instrument present. So they've just got a code that computes radiances in the water. They compute those, compare them with Hydrolite. Okay, it agrees to within 1%. Then Howard Gordon had a paper back in '92 where he was looking at instrument shadowing from a simple radiometer that was like this in the water, and then it was looking out at some delta omega. So sun's over here, you get a shadow like this, so there's a shattering effect on the LU value. So Howard had a Monte Carlo code where he computed